diagram it looks more like an open system, but here there is a piston that is fixed to this diagram. Now if you take a look at this, you see that there is a chemical reaction taking place between dilute hydrochloric acid and zinc. But of course, in the production of hydrogen gas, if you react a very reactive metal with a strong acid, you will get hydrogen gas at the end of the day. Whether it is sulfuric acid or it is hydrochloric acid or even nitric acid, once a strong acid is allowed to react with a very reactive metal like zinc, you will definitely have hydrogen gas. Now, in a process where hydrogen gas was supposed to be produced, okay, and then you choose to mix zinc and hydrochloric acid, and there is a piston that is fixed to a particular cylinder, you will notice that once the hydrochloric acid is turned into that particular cylinder that contains zinc, hydrogen gas will be produced. There will be a pressure that is coming from the hydrogen gas trying to counter the air pressure, holding the piston firm in the cylinder. So as the hydrogen gas is produced, it tries to force the piston upward. By doing so, work is done by the system, and it means that the volume at this kind of a time will begin to do what? Will begin to change. So at this point where hydrogen gas is produced, creating work to be done, work which is done by trying to force the piston upward to move against the air pressure, allows you to talk about internal energy. And that is just it. You can see that if you wanted to calculate anything that is happening around this system, you will notice that the result you will get will differ from this result. Now let's take a look at this result. In this result, everywhere is sealed, and then hydrogen gas is emptied into the granules of zinc. Sorry, sulfuric acid rather. Hydrogen gas at this point is also produced, but hydrogen gas at this point is having a constant pressure. At this point in time, hydrogen gas is not performing any work because it's not moving anything inside it. At this point, work is not done. Pressure is constant. We are calculating enthalpy of reaction. And the result we will get at this point, where work is not done, refer yourself to the first law of thermodynamics, where work is not done, work is constant. You have only enthalpy and heat of a reaction. That is it. So you could see that where a system that has the same reaction taking place with the same reactant will be giving you this different result for enthalpy and different result for internal energy, because volume is set constant in one, and then pressure is set constant in one. One where volume is set constant, work is done. One where pressure is set constant, work is not done. Even though both of them are state functions and both of them are talking about heat changes. At least you should understand now that when you talk about internal energy of a system and enthalpy of a reaction, you are not talking about the same thing. Even though both of them have similar properties, like being members of a state function and also talking about heat changes. But you are not talking about the same thing and will not get the same result. Now we can relate that. We can relate enthalpy, internal energy, and the work that is done in a system. We can relate that. Now let me take us down memory lane. Now permit me to just put this off. Let's take ourselves down memory lane. Now, do you know that for any thermodynamic system, okay, where there is a change in volume, okay, against a pressure at where you have compression, okay, or rather where you have expansion of gas, expansion of gas. all right, you have an expansion of a gas, which will definitely result to what? A change in volume, okay, against pressure, because expansion has to do with pressure. So if you have pressure in terms of expansion, the volume of the gas will change. So we have this, we also have pressure involved. It is only at the point where you have expansion of a gas with respect to change in volume, you can talk about work that is done. In that case, work done will be equals to these two, which is P change in V. In sum, it is negative P change in V. That means for work to be done, there must be a change in what? In volume with respect to expansion of a gas. And if this is true, then you can relate this to the first law of thermodynamics, which actually says delta H is equals to delta U, okay, plus P change in V. Where this, of course, this will have been W. Where, of course, delta H is equals to delta U plus what? P change in delta V, which is this. So suiting this to this equation here. But now, always, when you talk about internal energy and enthalpy, we are talking more of gases. So where gases are involved, then you have to relate what you are talking about to your simple ideal gas equation where gases are involved. Now, if we were relating this to gases, we will have that for gases, we know that PV is equals to nRT. Of course, that is this. PV is equals to nRT. For gases, introducing N, the number of moles of gases. So you can actually be able to calculate the number of moles of gases for reactants and number of moles of gases for products, which means you have two different calculations to make. So for the number of moles for gases for a reactant, we'll have that P V of reactant is equals to N of reactant root T. And then you also have P V of product is equals to N P, which is product, root T. If you subtract this equation from this one, that is subtract the reactants from the product, you'll get a result. Now if you subtract this equation from this one, know that this P is constant and this root T is constant. So we're going to have something like P in parentheses Vp minus V arrow is equals to root T Np minus N arrow. That is the subtraction because we are subtracting reactant from the product. In that case, this, and this is changing N and this is changing V. So it's something like saying P change in V is equals to changing N root T. That is what you're having. It brings you back to P change in V in this your equation. It means that W is changing N root T. So you substitute this equation for this in this one, you will have that. You will have that. Therefore, from this, I'm moving here, substituting this into this equation. So it means that you will have that delta H is equals to delta U plus delta N RT for a gas. And this is the relationship between enthalpy and internal energy for a gas system. So if someone asks you to define internal energy and enthalpy, to state their differences, and write an equation that shows the relationship between the two for a gaseous system, this is all that is needed from you to do, for you to do. You can see that this is quite short, quite simple, and it's not complicated. So if you follow it step by step, you will easily understand what we've done here. It's been a very wonderful moment having this class with you. Today I'm sure you have been able to understand what internal energy of a system is, what it does, how it make work possible, what enthalpy of a reaction is, how are the two